Good morning, sir. My name is Astha. Today I'm going to present my assignment number 2. In this slide, I'll explain the correlation causation, which is one of the most common reasoning error. Correlation means that two things are seen together or changed together. However, causation means that one thing directly produces the other. The mistake happens when we observe a relationship and immediately assume that one variable must be the cause. So from the definition, we can see that correlation causation confusion happens when two variables are related and we wrongly conclude that one directly causes the other. A correlation may arise because of the coincidence, reverse causation, or a third hidden factor. In the research example shown here, higher catalyst surface area is associated with higher yield. At first, this may sound like a casual relationship, but that conclusion may be too quick. The real reason for the better yield could be something else, such as active site density, metal dispersion, or some other hidden factor. So the correlation is real, but the cause may be different. And in the daily life example, it makes this easier to understand. People carrying umbrellas are often seen on rainy days, but umbrellas do not cause rain. Both are connected to a third factor, which is the weather. So this fallacy teaches us to be careful before claiming cause and effect. In science, especially, correlation may suggest a hypothesis, but it is not proof of causation by itself. The next fallacy is the post hoc fallacy. The phrase means after this, therefore, because of this. Like by definition, we can see it occurs when we assume that because event B happened after event A must have caused event B. So this kind of reasoning is common because our mind naturally looks for patterns and explanation. In the research example, product yield improved after changing the solvent. So the solvent is claimed to be the reason, but this is not necessarily true. Other factors may also have changed, such as temperature, substrate purity, stirring rate, or even experimental conditions. So simply observing that improvement came after a change does not prove that the change caused the improvement. The daily life example is very familiar. Like someone says, I took a vitamin C tablet and after 2 days my cold improved. So the tablet cured me. But in reality, the cold might have improved on its own as part of the normal recovery process. So the lesson here is that sequence does not automatically mean causation. In scientific work, controlled experiments are necessary to test true cause and effect. This slide is about cherry picking. Cherry picking means selecting only the evidence that supports our claim while ignoring evidence that weakens or contradicts it. It is a serious problem because it creates a biased picture of reality. Even if the selected evidence is true, the conclusion may still be misleading if important contradictory evidence is hidden. In the research example, only the best catalytic cycles are reported while failed substrates or low-yield trials are left out. This makes the catalyst look more effective and general than it may actually be. In research communication, this is dangerous because it affects reproducibility and can mislead other scientists. In the daily life example, it is reading only reviews that support a product we already want to buy. This is something many people do unconsciously. Instead of gathering balanced information, we focus only on what confirms our preference. So, cherry picking shows how incomplete evidence can be just as misleading as false evidence. Good scientific reasoning requires us to consider the full data set, not just the convenient part of it. Here we have false dichotomy, also known as false dilemma. This happens when a situation is presented as if there are only two extreme options, when in reality there may be many possible alternatives in between. This kind of argument is persuasive because it simplifies complex issues into easy choices, but that simplification is often misleading. The research example says either this drug is completely safe or it should never be used. That is clearly an oversimplification. In reality, many drugs have side effects but are still useful when prescribed in the right dose for the right patients. under the right medical supervision. So safety is often a matter of balance, not a simple yes or no category. The daily life example says either you agree with me or you do not care about the country. This ignores the possibility that people may care deeply and still disagree about the best solution. So the lesson is that forcing a complex issue into only two choices can distort reality. In scientific and ethical discussion, nuance is essential. This slide explains circular reasoning. So by definition, circular reasoning occurs when the conclusion is used as evidence for itself. The argument does not provide independent support, it simply repeats the claim in another form. So circular reasoning happens when the conclusion is used as evidence for itself. In other words, instead of offering independent support, the argument simply repeats the same claim in another form. So this makes the reasoning sound complete, but actually nothing new has been demonstrated. So here we have the research example in which a researcher says this theory is true because it is the correct explanation of the data. And we know it is the correct explanation because the theory is true. This is circular because the statement loops back without offering fresh evidence. So the theory is said to be true because it correctly explains the data, and then it is said to explain the data because the theory is true. So this is circular because the statement loops back to itself. It does not provide external validation, experimental proof, or any independent support. Also, we have this daily life example which says, I am trustworthy because I always tell the truth, and I always tell the truth because I am trustworthy. The second part just repeats the first in a different way, so nothing new is proven. So again, this sounds convincing at first, but when we examine it carefully, we see that the claim is simply repeating itself. In science, circular reasoning is especially problematic because theories must be supported by evidence, not by restating the conclusion. So this slide gives this general definition of logical fallacies and cognitive biases. Logical fallacies are errors in reasoning or in the structure of an argument. They often sound plausible and persuasive, but the conclusion does not logically follow from the premises. The important point is that a fallacy is usually visible in the argument itself. We can often identify the exact sentence or step where the logic breaks down. The example given here is circular reasoning. This catalyst is excellent because it gives good yield, and we know the yield is good because the catalyst is excellent. So this argument does not provide any independent evidence, so it is logically weak. Logical fallacies matter a lot in research communication because science depends on strong reasoning. If the reasoning is flawed, then even a well presented conclusion may be misleading. So, recognizing fallacies helps us evaluate both scientific claims and everyday arguments more critically. This slide introduces cognitive biases also. Cognitive biases are systematic errors in thinking and judgment. They arise from the way our mind processes information using shortcuts, prior beliefs, emotions, and habits. Unlike logical fallacies, which are often visible in arguments, cognitive biases usually work in the background. They influence how we interpret information before we even express a conclusion. For example, the slide mentions confirmation bias. If a researcher strongly believes that their catalyst is superior, they may unconsciously give more attention to the positive results and less attention to the negative ones. Uh, this does not always happen intentionally. That is what makes bias so important. It can influence judgment even when the person believes they are being objective. So, cognitive biases affect what evidence we notice, how we interpret it, and what we remember later. In research, this can influence the design of experiments, the interpretation of results, and even publication choices. That is why awareness of cognitive bias is a major part of professional ethics and good scientific practice. This slide summarizes the difference between logical fallacies and cognitive biases. Logical fallacies are errors in argument structure as we have seen earlier. They appear mainly in what we say or write, while cognitive biases, in contrast, are errors in thinking and judgment. They shape how we perceive and interpret information, often unconsciously. A simple way to remember the difference is the line written here. Biases distort how we think, and fallacies distort how we argue. This is a very useful distinction because in real life, um, the two are often connected. A person may first be influenced by a bias and then express that distorted thinking as a fallacies are. So, in practice, if we want to improve scientific reasoning, we must work on both levels. We should check the structure of our arguments to avoid fallacies, and we should also reflect on our mental habits to reduce bias. Good science requires both logical clarity and self awareness. So, here I have written biases distort how we think, and fallacies distort how we argue. This line can simply differentiate both logical fallacies and cognitive biases in a simple words. Now, I will apply these ideas to the first everyday claim: jaggery is healthier than sugar. This statement is very common, especially because jaggery is seen as like more natural, more traditional, and less processed than white sugar. Because of that image, many people assume it must be healthier option. So, like it is true that jaggery may contain small amounts of mineral, but it is still high in sugar and calories. So the statement is too broad and a little misleading as it is written in the slides. So like it uh, it means that jaggery may contain small amount of minerals. However, that does not automatically make it a healthy food. It is still high in sugar and calories. The claim becomes too broad when it simply says healthier without qualification. The logical fallacy here is hasty generalization because a limited difference is being turned into a much wider health conclusion. The here cognitive biases we'll talk about involved is naturalness bias or halo effect. Like people often associate natural or traditional foods with overall goodness. The gap in quantitative reasoning is also important. The statement does not compare actual calorie content, sugar load, glycemic effect, or the true magnitude of the mineral advantage. So the balanced conclusion is that jaggery may be slightly less refined, but it is not automatically healthy or universally better than sugar. So here we applied our ideas to the first this everyday claim: jaggery is healthier than sugar. Now we have two more statements. The second statement is like caffeine is dehydrating, therefore drinking coffee is not healthy. At first, this sounds logical because caffeine is known to have a mild diuretic effect, but the conclusion goes much further than the evidence actually supports. Like research shows that moderate coffee intake does not significantly dehydrate regular coffee drinkers and can still contribute to daily fluid intake. Moderate coffee intake does not significantly it means that moderate coffee intake does not significantly dehydrate regular coffee drinkers, and coffee can still contribute to daily fluid intake. So even if caffeine has some diuretic action, it does not follow that coffee as a whole is unhealthy. That is why the logical fallacy here is non sequitur. The conclusion does not properly follow from the premise. Here, the cognitive bias is a negative bias here because one possible negative effect is used to judge the whole drink. One potentially negative feature is taken and used to judge the entire beverage. There is also a gap in quantitative reasoning because like we can see there is a gap in quantitative reasoning because the statement ignores the amount of caffeine consumed. Like we have more factors like the number of cups, individual sensitivity, and the difference between mild diuresis and true dehydration. So, a better conclusion would be that excessive caffeine may cause problems, but moderate coffee consumption cannot be dismissed so simply. Now, we'll move further to our last statement. Next slide. The third statement says medicines based on plants and natural products are better and safer than synthetic pharmaceutical products. So this is a very common belief because people often associate natural with safe. But in medicine, safety does not depend only on whether something is natural or synthetic. It depends on dose, purity, side effect, drug interactions, and proper testing. Like in other words, this belief is a very common because many people feel the natural things are gentle, pure, and less harmful. But in medicine, that assumption is not reliable. Safety and effectiveness do not depend only on whether a compound comes from a plant or a lab. They depend on the number of factors like dose, purity, side effects, etc., like mechanism, drug interaction, and proper testing. Many natural substances can be toxic, and many synthetic drugs can be very safe when used correctly with correct prescription. So, the logical fallacy here is appeal to nature. The assumption that natural automatically means better. The cognitive bias is naturalness bias because people tend to trust plant-based or traditional products more easily. The gap in quantitative reasoning, here is the gap in quantitative reasoning, which is that the claim provides no data on toxicity, therapeutic dose, efficacy, adverse effects, or clinical outcomes. So the the scientific position is that both natural and synthetic medicines should be evaluated using evidence, not judged only uh, by their like origin. I, I mean, so the like scientific position is that both natural and synthetic medicines should be evaluated using evidence, not judged only by their origin. Before moving to the examples of retraction of papers, we will first see what the retraction of scientific papers actually means. So, retraction is the process by which a journal formally withdraws a published paper from the scientific record when its findings are no longer considered reliable. It doesn't mean every mistake leads to a retraction, only serious problems that cannot be fixed by a simple correction will lead to the retraction of a scientific paper. There are two broad reasons. One is honest error, for example, major mistakes in data analysis or method that once discovered change the main conclusion of the study. The other one is the research misconduct, fabrication or falsification of data, plagiarism, duplicate publications, unethical experiments, or even manipulation of citations. Retraction can be initiated by the authors themselves when they realize a serious error or by editors and publishers after concerns are raised and investigated. The journal then publishes a retraction notice explaining that the article should not be treated as part of the reliable literature and giving the main reason. Although retractions sound negative, they are actually an important part of self-correction in science. They protect future researchers from building on incorrect or in unethical work and help maintain trust in the literature, even if they are sometimes embarrassing for the authors and the journal. So first case I have taken is a good example of how an exciting paper can end up being retracted when its central claims turns out to be wrong. So this example is from retracted paper which was published in Nature Catalysis. So the original work reported a cross-coupling reaction that was advertised as completely metal-free. In the other words, the author claimed that they could achieve a transformation similar to a classic palladium-catalyzed Suzuki-type reaction without using any transition metal catalyst at all. Because palladium is expensive and there are concerns about metal residues, such a claim is extremely attractive and immediately drew attention when the paper appeared in a high-impact journal like Nature Catalysis. So after publication, other research groups started to reproduce and study this metal-free system in more detail. At first, they could get the reaction to work when they followed the original procedure, but they began to suspect that some invisible catalytic species might be responsible. Several independent teams that then carried out careful control experiments and metal analysis. They discovered that the reagents and additive used in the original work, such as bases or other salt, contained tiny, previously undetected amount of palladium. Even at levels as low as parts per billion, palladium is such a powerful catalyst for these couplings that it can drive the reaction efficiently. When those groups removed or rigorously minimized palladium contamination, for example by purifying reagents, changing suppliers, or adding metal scavengers, the supposedly metal-free reaction stopped working. This clearly showed that the transformation was in fact palladium catalyzed and not metal-free. These results were published as detailed follow-up studies, including several matters arising papers in Nature Catalysis about 11 months after the original article. All of them converged on the same conclusion. The key claim of the initial paper was incorrect because trace palladium impurities were the real catalysts. That meant the main novelty of the work collapsed. The paper no longer represented a new class of metal-free catalysis. Instead, it was another example of how sensitive these reactions are to tiny amounts of palladium. A simple correction could not fix this because the error affected the central mechanism and the interpretation of the active species and the way the entire reaction was presented. In response to this strong body of evidence, the authors and the journal decided to retract the paper. Through the retraction, they formally acknowledged that the reaction does not proceed under truly metal-free conditions and that the original mechanistic claim cannot be trusted. This decision was important for the scientific record. Other chemists might design new research projects or industrial processes based on the idea that such couplings can genuinely run without metals. Leaving the paper in the literature would therefore mislead future work and give an inaccurate picture of what is really possible. Finally, this case is part of a broader pattern highlighted in the article Metal Free. The mistake that chemists seem doomed to repeat. Several earlier reports of metal-free or iron-catalyzed coupling have later turned out to be driven by the trace palladium contamination. The ethical lesson is that the extraordinary claims such as replacing well-established palladium catalysis with a metal-free pathway need very strong analytical support, careful must analysis, strict controls, and robust mechanistic studies. When follow-up work shows that these conditions were not met and the main claim is wrong, retraction becomes the most honest way to correct the literature and prevent way to correct the literature and sorry and like most honest way to correct the literature and prevent the community from repeating the same mistakes again and again. Now we'll see next example, which is this slide explains another example of retracted paper, which is from Dalton transaction. So it highlights the kind of scientific concerns that can lead to serious doubts about a paper. In this example, the issue concluded discrepancies in elemental analysis, doubts about validity of the proposed complex structures and oxidation states, and question about the proposed catalytic mechanism. These are major concerns in chemistry because they affect the foundation of the paper. If the elemental analysis does not match, then the identity or purity of the compound becomes uncertain. If the structure or oxidation state assignment is questionable, then the chemical interpretation also becomes weak. And if the mechanism is not supported by sound evidence, then the explanation of the reactivity becomes unreliable. I hope it connects the dot. So this example shows that retraction is not always about one simple mistake. Sometimes it is the result of multiple scientific weaknesses that together make the conclusion difficult to trust. The third example is a example of a retracted a review article. So this slide gives another example where the issue was not only scientific confidence but also publication ethics. According to this retraction, the paper was retracted at the request of the editor and the publishers. Research integrity and publishing ethics teams investigated the article. The investigation found that 8 citations in this research article had been added that were not relevant to the topic of the paper. Because of this, the editor lost confidence in the findings and the article was formally retracted. This is important because citations are supposed to support the argument and connect the paper to genuinely relevant previous work. If relevant citations are added, it raises concerns about integrity, transparency, and the reliability of the publication process. So through these examples, the main message is that research ethics includes much more than avoiding plagiarism. It also includes accurate characterization, honest interpretation, appropriate mechanism proposals, and the responsible citation practices. So these retracted papers example shows that when scientific reasoning and ethical standards are compromised, the final outcome can be loss of trust and even retraction. That's all. Thank you.